So as we continue here, again, it's the amount of water that's present that will control which side of the equilibrium this reaction falls on. If we have a large amount of water present, then the reaction is going to go in reverse and favor the original carbonyl. But recall that the water is a byproduct in this middle step. And so if we're able to remove one of the products, then we favor the forward reaction. So if we manage to remove water during the reaction, then we favor the hemiacetal, or more often the acetal or ketal. Now, there's a number of different things that this reaction can be used for. And this reaction actually has a number of advantages synthetically. One of those roles is what we call a protecting group. So protecting groups are groups that basically hide a functional group so that you can do something else in the course of a synthesis. If you think about some of the examples we talked about previously with synthesis, a lot of organic synthesis, we have, multiple functional groups, very complicated molecules. And sometimes you need to hide them. And so let's say that we wanted to add a nucleophile to this ester. And we're going to learn about, in the near future, the types of reactions you can do with esters. The problem is that the ketone is often going to be a better electrophile. So what do you do? Well, if you can hide the ketone, and one way you can do that is to make it into a ketal. Now that carbon of the ketone, or what was the ketone, is no longer a good electrophile because the carbonyl is gone. And so if you add a nucleophile now, your nucleophile will attack only the ester, and then in a future step, you can get rid of the ketal and get your carbonyl back. And that's sort of a very quick overview, very simple example of what we refer to as a protecting group in organic synthesis. But for our purposes, what we might view as the most important reaction or most important application of this reaction shows up in carbohydrates. And we'll show one example here using glucose. So here's glucose. We're going to draw it in its Fisher projection. And as you go on to take biochemistry, this is a process and a reaction that you'll learn a lot more about. But often with a lot of sugars, glucose especially, but many of them, they often are more commonly exist in a cyclic form. And what that cyclic form looks like is the following. So it's a six-membered ring. That looks something like this. Now, how do we get from one form to the other? Well, if we look carefully at this cyclic form, right here we have what is the hemiacetal of the open form of glucose. And that forms from this alcohol doing a 1,2 addition into this carbonyl. And once that happens, we get the cyclic form, the hemiacetal, and that gives us the interconversion with the closed form of glucose. And again, this is a reaction that's very common for sugars, and we often find sugars not in their open form, but in their closed form, which exists as hemiacetals. All right, our final group of nucleophiles for this chapter, this section, are to look at nitrogen nucleophiles. And we're going to start with one sort of very special case, and then we'll get into more general cases of amines. But the one special case is known as the Wolff-Kishner reaction. So the Wolff-Kishner takes an aldehyde or a ketone and uses this reagent known as hydrazine, which is just two NH2 groups put together, a base such as KOH, and then high temperature. Typically have to heat these over 200 degrees Celsius. But as a result, the carbonyl is actually removed completely and replaced by a pair of hydrogens. Now, the hydrazine here is actually a surprisingly good nucleophile. And the reason for that is you have these two nitrogens right next to each other, and both of those nitrogens have lone pairs. And that's a situation the molecule doesn't really like. It doesn't really like having those lone pairs next to each other. And so it prompts, one of them to want to get rid of its lone pair and donate them and react. All right. How does this work mechanistically? So the first step, probably not going to be any surprise, but our nitrogen nucleophile adds into the carbonyl. Giving us, as we've seen so many times before, a tetrahedral intermediate. This tetrahedral intermediate will now undergo a proton transfer. Given we have this negatively charged oxygen, it's going to be happy to accept a proton from this positively charged nitrogen. Giving us that intermediate. Now, here's where the mechanism is going to get a little bit unusual. Because the nitrogen is going to add in its lone pair and kick out the leaving group, hydroxide. Now, why do I say that's a little bit unusual? Well, we've said many times before that hydroxide is a terrible leaving group. And all of a sudden, we're saying it's okay. Well, it's not necessarily that it's okay here. It's the reaction conditions that matter. What do I mean by that? Well, if you think back to the previous page and what I wrote down, the reaction temperature is 200 degrees Celsius, which means we've got a lot of energy, and that's a lot of energy that can overcome activation energies for some pretty unfavorable processes. So that 200 degrees is able to overcome that really bad leaving group. Now hydroxide can come in. It removes one of these hydrogens. Electrons shift over. Oops, let's not skip a step. So that positively charged nitrogen will lose a hydrogen. What removes it? Most likely a molecule of hydroxide comes in and removes it. And then we get what I was starting to show, which is another molecule of hydroxide removes the hydrogen. Electrons shift over, and we pick up a proton from water. All right, not quite done yet. Now this same step we just had, the hydroxide removing one of those protons, is going to repeat itself. And this, it turns out, is the step that drives the reaction forward. You'll notice every other step I have here, I've shown as equilibrium, but not this last step. Why not for this last step? Well, this spits out our product, which is just an alkane. But what's the byproduct that we got here? Nitrogen gas. This step is irreversible. Why is it irreversible? Well, there's a couple reasons why it's irreversible. First, as a gas, as soon as nitrogen forms, it just evaporates out of the solution. Second, nitrogen is pretty much completely inert. I think we've said previously that we often use nitrogen in organic chemistry as an inert atmosphere for a lot of different reactions. So once that nitrogen is left, it's not going to add back in, and the reaction is done.